Hi everybody, welcome back to Chem 140. As you can see on the screen, this is one of those very rare times where there are no upcoming assignments. There's no lab due this week, there's no quiz posted to do. If you took the exam yesterday, which was like 90% of the class, then you're all done with that. I looked at the scores very briefly and they looked pretty good. Just a little clarification on why the exam doesn't show your score. So there's two reasons. One, if you know your score, then you can communicate to other people how well you did and share your answers. So that's obviously not something that I intend for you to do. Um, so I don't release scores until after everything is done. The second thing that the second reason that I don't release the scores right away is because Canvas doesn't know how to do extra credit. So the exam actually has 10% more points than possible. So it's out of 75, but if you saw on the screen how many points it was worth, it said 83. What Canvas will do is it will take your score out of 83, turn that into a percentage, and then move it over to the gradebook as a percentage, and it won't go over 100 because it doesn't know what to do. So what ends up happening is everybody gets a really low score, and they're like, why did I get a score in like the 70s when you should really have like a score of 85% or whatever. So I have to manually go back and adjust all the scores. It should show up currently as just completed. If it says completed, then you're good to go. I do realize that there were a lot of Canvas errors yesterday. I got like 5 or 6 emails from students saying like, "Hey, I hit submit and I got an error. Did it go through?" And in every case, it did go through. So I don't know. It's Canvas. Canvas is a piece of shit, and I hate it, but it's what we got. Um, where are we? Let's see here. Oh, I'm in the wrong screen. I want to be in that one. So if you have any questions about the exam, let me know. I can't release scores until at the earliest tomorrow. Once I have everybody's exam in. If you have not taken the exam yet and it says closed for some reason you didn't take the exam, email me immediately so that I can figure out what to do, because missing an exam pretty much guarantees you can't pass the class. It's just too many points. Like, it's 75 out of your 500. It's a lot. All right, what are we doing today? We're going to talk about bonding. I'm also going to try and stay hydrated because I'm really bad at that. I just noticed something in my screen here. Hold on. What did I do? There we go. I'm trying to learn how to use this program better that I'm streaming. And the other day I was moving stuff all over the place and like, I don't want to do that. Well, I can apparently prevent it from doing that. So I'm trying to lock some of these elements in place here. Okay, so we're going to talk about bonding. Bonding is the term that we ascribe to the force that holds atoms together. So there are many fundamental forces in nature. Any force that causes two atoms to be, or ions, to be held together and require an input of energy to separate them, we're going to call a bond. There's a bunch of different types of bonds, as you could probably surmise. And the purpose of Chapter 9 is to look at ionic bonding, and the purpose of Chapter 10 is to look at covalent bonding. And you see at the bottom of the section, in Section 9.4, we're going to have like a little segue where we go from what's ionic to what's covalent so that we can lead into the next section. But in order to talk about bonding, we need to talk about some fundamental properties of atoms, such as how many electrons there are, their structure, etc. Well, in 140, we don't really do that. We sort of hand wave over it a little bit. But we have a shortcut that will be useful for us. And of course, you're going to need your periodic table to do this. So go ahead and go to P table right now if you've got it. Let's talk a little bit more about bonding. So like I just said, a bond is going to be any interaction that holds two atoms together. You get to see your scores when I release them, which I said will be at the earliest tomorrow. Okay, so we'll do... So we'll include that. Ions are also eligible to be bonded. In fact, in ionic bonds, atoms have to be charged, so they have to be ionic. Now, the factor that is involved in bonding is this right here, the electron. And the reason for this is actually pretty simple. If my atom is right here, and I interact with another atom, what parts of the atom will encounter each other first? Well, here's the nucleus, this part in the middle here, right? And on the outside, we have the electrons in the electron cloud. And I'm just putting a random number of protons and electrons here. So, of the two entities, which two will collide with each other first and interact? Well, it turns out it's the electrons. So the electrons on the outside of two atoms will come into contact with each other and have an interaction. Generally, that reaction is repulsion, because electrons are both negatively charged, and negative things repel other negative things. But if you were to cause these two things to collide into each other at a very high speed, then the electrons might get scattered everywhere, and you might have a new arrangement when you're done. And so that's how bonds form, is from these crazy collisions at really high energy that overcome this repulsion and create a new, more stable arrangement of electrons around the atom. Now, there's two different models that we use to describe how electrons get quote-unquote used in a bond. And so the first method is called the ionic bonding method. In an ionic bond, we transfer electrons from one atom to the other to create ions. When you do that, you create entities that have an overall charge, and then those overall charges are attracted to each other. In a different model, the covalent model, what ends up happening is we share electrons between two species. There's a collision, the electrons rearrange their position in space. They tend to be generally in one area more than the others. And we'll draw pictures of those later on when we get to them. So that'll be Unit 10, which we'll do on probably Thursday or maybe tomorrow, depending. All right. And that's what that says right there. Now, where do electrons live? We have not talked about this at all until this point, and in fact, we don't really talk about it much after this screen here. In Chem 161, we're going to talk about how electron structure is organized in a lot of detail. We're going to talk about SPDF orbitals, counting valence electrons, how we determine like the distinguishing electron, all of that stuff. If you are reading sources online and you see anything that refers to like, oh, this is an S electron or this is a P electron or whatever, we're not going to cover that in this class because it doesn't help us for bonding at the level that we're going to work at, which is a very simple level. We can get away with figuring out how bonding works by just counting patterns in electrons. Now, in quantum mechanics, when we talk about electrons get arranged in these sorts of rings as shown on the screen, like abstractly. Now, electrons don't actually sit on rings like our planet is on an orbit around the sun. But you can think of these as just like, this is a progressively larger and larger electron cloud, or a larger volume for my electrons to sit in. And I'm just I am circling the last of these in each case. An interesting feature is that every time we go down a row on the periodic table, we add another layer of electrons called shells. in these diagrams, we're sort of representing each of these shells as a ring. Now, the rings only have so much space before we have to start a new ring. And in general, what ends up happening is that, with the exception of the first one, we tend to go up to 8 electrons and then start making a new ring. And then we do some other funky, crazy stuff because quantum mechanics. 8 is sort of the magic number. And all of these elements that we have chosen here, so we've got fluorine, chlorine, bromine, and iodine, these are all elements that are right next to the noble gases in column 17, group 17. The electrons stay within the cloud. This chapter and Unit 10 should be assigned for next week, yeah. So suffice it to say, since this is all very hand-wavy and I'm kind of ignoring any of the details here, that atoms have lots of electrons buzzing around them. And they sort of arrange themselves in these layers. Some are closer and some are farther. The ring's not really a perimeter. It's more of an average. So on average, the electrons in this second layer will be about this far away. Because they can be any distance that they want to. Kind of like if I throw a ball up into the air. If I throw it hard enough, it'll go all the way up to the edge of the atmosphere. But it will eventually come down. But on average, people who throw a ball, it won't go higher than like 20 feet. With electrons, it's the same way. They can go anywhere that they want to. They're buzzing around the nucleus, but they're attracted to the nucleus, so they always come back. Except, you know, when they don't in a chemical reaction. So we got all these electrons here, and we're separating them into the rings, and there's always going to be a ring on the outside. We're going to give that outside layer a special term. We're going to call it valence electrons. And the reason that we care about the outside layer of electrons is for the same reason that we had that diagram before. If I have two atoms that bump into each other, the electrons that are on the outside are going to be the ones that actually see each other. Whereas the stuff on the inside doesn't. The reason being, these electrons repel each other, and so they don't really even interact with what's on the outside. So only the outermost electrons, the valence electrons, are going to engage with other electrons in an atom that bonks into it. Oops, I didn't mean to actually. I didn't think that there was text appearing there. So we need to figure out, without going into extreme detail, how many electrons are on the outside of an atom. And it turns out, excuse me, there is a very easy way to do that. And that requires the periodic table and for your cat to stop yowling at you. What is going on over there? I hear her, but I don't see her. Where are you? I don't know. She's probably okay. Alright, so the number of shells, again, these rings that we have going around the outside, is equal to the period number. But the number of electrons in the outermost shell is going to be equal to the group number. So this is why periods and groups are important. They tell us a lot about how electrons are structured. So for instance, fluorine here is, oops, that's the wrong pen. So fluorine here is in period 2. So it must have 2 layers. That didn't quite... I thought that would be a little more clear here. Let's do it this way. So we got 1 layer, 2 layers. It's in group 7A, so there must be 1, 2, 3, 4, 5, 6, 7 valence electrons. There you go. So that's how we count valence electrons. We're going to look at what group an atom is in and use its number. Now, of course, there is a issue with this. This designation only works for elements with a group designation that has an A in it. Now, depending on your periodic table, you might not have the A designations at all. So what that boils down to is that, so this is for groups 1 and 2, and then 13 through 18. After you remove the 10. So if you look in group 1, those atoms have 1 valence electron. If you look in group 2, they have 2 valence electrons. Then you got to skip all the way over to 13, because that's the next A group element. And for 13 through 18, you get rid of the 10, and the number that is left is how many valence electrons you have. Now you can see that all the elements that are on the screen here, fluorine, chlorine, bromine, and iodine, those are all in group 17. I get rid of the 10, that gives me a 7. They should all have 7 valence electrons, and it turns out that they do. Now, I'm sure that there are other questions. For example, wait a second, if 8's the magic number, why the heck are there more than 8 in here? In fact, there should be 18. And I don't want to actually count these. Yeah, there are 18. Why does this happen? And the answer is... we're going to talk about that in 161 and also 361. So... electronic structure is weird, and for the purposes of this class, you don't need to know it. All we care about is how many electrons eventually end up on the outside, and those are the valence electrons, and you do that by counting the group number. Alright, so let's do an example. Oop, I don't know why my text went over here into the banner. So what I wanted to do is figure out how many shells of electrons are around phosphorus and count its valence electrons. So if we go to the periodic table, and we look at phosphorus, we can see it's in period... I'm not actually looking at the table yet. It's in period 3. So there will be 3 layers of electrons. It's also in group 15, or 5A. So that means it has 5 valence electrons. So if I was to draw a phosphorus atom, and I would draw all its electrons around it, I would put 5 dots around it for 5 electrons. Now, this is to match up with the picture on the previous slide. What we're going to do in just a second, we're going to talk about Lewis symbols and structures, which are going to actually change what we're drawing here so that it looks more like this. So if you've done any chemistry before and you're like, well, wait a second, why didn't you pair them? We're going to get to that. All right. This one I'm going to have you try. So I want you to tell me what valence shell, the number of valence shells, And how many electrons are in O with a minus charge? How do I get my oxygen atom to have a minus charge? I'd have to change the number of electrons. So, tell me how many valence shells and how many valence electrons O minus has. Yeah, you can play around with p-table and see what the electron clouds look like. It's probably not going to be super helpful other than like a curiosity to you right now. But that being said, that will help you later on. Also, if your browser is as like bogged down as mine is, rendering these models of electrons takes forever. Oh, and then the site will crash, so that's nice. Alright, so if I look in the valence shell, oxygen is in period 2, so it must be 2 shells. And then the number of electrons in there. Normally it would have 6, but to make something with a negative charge, I have to give it an additional electron. So there should be 2 shells and 7 valence electrons. And there is. Now this one is actually a little bit more tricky. What's the valence shell and number of electrons for calcium if I remove 2 electrons from it? I'm going to let you think about this for just a second and see if you can come up with the right answer. Yeah, if it's in period 4, there should be 4 shells. But, what are we doing to calcium when we make it positive 2? Yeah, we took away 2 electrons. How many electrons were in shell 4 to start with? Yeah, you end up with 0. What the heck do you do then? So, we know that there are 4 shells. 1, 2, 3, 4. And in the 4th shell, we have 2 valence electrons. So if I get rid of these, boop, there goes the last shell. How many shells does this have now? Yeah, it only has 3, huh? Interesting. So this would have 3 shells and not 4 because we removed a shell. And then how many valence electrons would it have? Well, what element does it look like when it's calcium 2+? This would have 18 electrons total, which is the same as argon. Well, if I look at argon on the periodic table, how many valence electrons does it have? Well, it's in group 8. So what that must mean is that the previous layer before we started putting on these extra ones in this outer layer out here, the previous layer must have had 8 valence electrons because that element is in group 8. So that's exactly it. If you take away all the valence electrons from an atom, that shell just goes away. And now you have the previous shell. And you can count valence electrons from there. Since calcium looks like argon when 2 of its electrons are removed, we would say that it has 8 valence electrons. Now again, this is all for this specific ion. For a 2+ ion. So this is just what happens if I'm removing electrons. It's possible to completely remove all the electrons in a shell. And if you do that, that shell is no longer the valence shell because there aren't electrons there. The previous one becomes the valence shell. So with cations, it's particularly weird. And every time I say cat, my cats are like, cat? And then they come in and bug me. So that's how we count valence electrons in both neutral atoms and ions. And for ions, either charge. So I'm going to put a bunch of these on the screen here. And what I want you to do is I want you to do the same process. Count the number of valence electrons and count the number of valence shells. I'm going to figure out why my cats are yowling. They had all morning to pay attention and to play, and now they just want to bug me. Yeah, Kresnik is in here just, he's like, I want to do anything other than what I'm doing right now. Now he's right here. Go ahead and do these problems, and I'm going to try and figure out why my cats are being cats. A cation is a positively charged ion, specifically, not an atom. All right, I'll be right back, and I'll give you about 3 or 4 minutes to do this. So see you in a bit. Oh, I've solved the mystery. Their food bowl was empty. All right, just a few more minutes, and we'll go over the answers. More like 1 minute or so. All right, let's go over the results for this. So if I look up arsenic on the periodic table, so it's in period 4, so it must have 4 shells. And it's in group 5, so it must have 5 valence electrons. We do the same thing for boron, so it's in period 2, so it's got 2 shells of electrons. It's in group 3A or 13, so it has 3 valence electrons. And we just do this for all the neutral atoms. Very straightforward. Now for ions, it's a little bit different. If I do just fluorine, then what I would do is I would say, okay, well, it's in period 2, so it has 2 shells. And since it's in group 7, I would say, oh, it has 7 valence electrons. But then when I take the negative into consideration, I'm going to add an electron. So the 7 becomes an 8. Same thing for barium. So barium is in period 2, 3, 4, 5, 6. So it has 6 shells. And barium normally would have 2 valence electrons. But then I do this to it. I make it have a charge of 3 minus. So I have to add 3 electrons. So 2 becomes 3 more, which is 5. For K plus here, potassium has 4 shells if it's just neutral, and 1 valence electron. But if I'm going to make it positive here, then I got to remove an electron here. So this becomes 0. You can't have 0 valence electrons, right? So we go down to the previous shell, and that becomes the new valence shell. And then finally for xenon, xenon's in period 3, 4, 5. I have to count it every time. I don't have these memorized. And because it's in group 8, it has 8 valence electrons. There you go. So that's how you count valence electrons for various atoms. Any questions, let me know in the chat. We're going to move on to the next section, which is taking this information that we've gathered and making a picture out of it. I think this is probably the most distinguishing thing that we do in chemistry. Like, if you have taken a chemistry class and I say, what do you remember about it the most? Everybody says, oh, drawing Lewis symbols. Like, it's a very visual, intuitive process that we've come up with to represent how atoms look. So I think that this is probably one of the more important things that we're going to do today, and possibly one of the most important things that we do this quarter. So let's talk about how to draw all of this information that we've discussed in a really convenient package that we can just show to other people. This is G.N. Lewis. He's important enough that somebody took a picture of him in his lab. And G.N. Lewis did a lot of experiments trying to figure out how atomic matter bonded together to make ions. And he thought, well, wait a second. If I make a lattice, maybe my electrons are arranged like a lattice. And he started drawing these pictures. And the pictures look kind of confusing, but what he noted was that everything seemed to revolve around the number 8. And so that there would be 8 valence electrons involved in whatever was going on here. And 2 things would bond together, 1 for 1, if they both added up to 8 valence electrons. So, for example, sodium, which has 1 valence electron, could bond with anything that has 7 valence electrons, which would be chlorine, bromine, iodine, fluorine, etc. What he did was he took these little cubic diagrams that he had in his notes and distilled that down into the simplest arrangement of electrons to what we're going to call the Lewis symbol, named after him. When will the lab be graded? When it's done. That's all I can say. How do you draw a Lewis symbol? Drawing a Lewis symbol is probably the easiest thing that we're going to do in this class. The first thing you're going to do is draw the atomic symbol. So that would be like O for oxygen, N for nitrogen, C, A for calcium, etc. Then you're going to put dots around the symbol. 1 dot per valence electron that you have. So if you have 2 valence electrons, you put 2 dots. If you have 8, you put 8 dots, and so on. And if you have an ion, there are special rules. We're going to put square brackets around it and add a charge to it. But drawing the Lewis symbol for something could not be easier. So let's do an example. We're going to draw the Lewis symbol for sodium. So step 1, draw the atomic symbol. Doink, there you go. You just write it somewhere on your paper. Step 2, draw a dot for each valence electron. Boom, there you go. That's it. It's not an ion, so we don't do step 3. That's the easiest thing that you could do in this class, probably. How the heck do I test you on this? I kind of can't. Not on Canvas. I can't make you draw a Lewis symbol in Canvas. That's not a thing I can do. Let's do oxygen. That's a little bit more involved here because it has more electrons. So the first step, draw the atomic symbol. Well, oxygen's atomic symbol is O, so we just do that. Then I'm going to draw a dot for each valence electron. Now, there's only 4 sides available to my diagram here. So if I go like this, 1, 2, 3, 4, I run out of space to put electrons pretty quickly. So once I do that, that's when I got to start pairing them together. So if you only have up to 4 dots, you just put 1 on each side and you're done. If you only have 2, you just put them wherever you want, on 2 of the 4 sides. But when you have more than 4, first you put them in individually, and then you pair them together, only after you've done that. Now, which 2 get paired doesn't matter. So if I had instead done this, those are my paireds and those are my unpaireds, that's okay. But if I had done this instead, this is not okay. And the reason for that, I just fed you. Why? Why are you like this? Oh, my goodness. The reason that you don't have this as a Lewis structure is because what do these electrons do to each other? Well, they're all negatively charged, so they repel. Something's going to fill in the space over here. And so the diagrams that we are drawing show that repulsion to the degree that it is able to do. Now, around something in 3 dimensions, there's more than 4 orientations. But it still turns out that electrons tend to arrange themselves in 4 regions around a central atom. So the Lewis symbol actually fairly closely represents what we observe in actual matter. Now, this isn't an ion, so we're going to skip that step. And that's the Lewis symbol for oxygen. So from the previous set of atoms, you know how many valence electrons that they have. What you're going to do is you're going to draw their Lewis symbol. So over here, we said that arsenic had 5 valence electrons. So I'm just going to go 1, 2, 3, 4. And I'll pair any one of them. There we go, 5. Now, for an ion, we're going to do the same thing. I drew that line too big. So we said that barium with a 3- charge has 5 valence electrons, but it is an ion. So if we have to do ions, you put square brackets down, and then you indicate the charge in the as a superscript after the ion. Okay? So I did these 2 for you. Draw the Lewis structure of the other 5. There's no way to post this in the chat when you're done, so when you're done, just let me know that you're done. And we'll go over the answers together in just a second. All right, looks like we have a few people that are finished, so I'll just quickly draw the answers here. So boron here has 3 valence electrons, so we'll just do that. Uh-oh. I hope your internet gets fixed soon. These videos are on YouTube forever, unless I get, like, copyright strikes, so... I can't imagine that my Mega Man 2 soundtrack that I'm going to be playing during the break is going to do that. So here's fluorine. I'm going to add the extra electron just in a different color here. A little darker here. So there it is. And because we added an electron to a neutral atom, it now has a charge of -1. I'm going to skip potassium for just a second. For xenon, we have 8 valence electrons because it's in group 8. So we're going to have all sides paired, and we're good there. Now, let's go do potassium real quick. So here's K. K has 1 valence electron, but what I'm going to do is I'm going to make it positively charged, which means that I remove the electron. And you might say, well, now wait a second, it has 8 valence electrons. Do I have to draw those in? And the convention that we adopt is that if you have 0 valence electrons, you just draw nothing. But we assume the next shell has 8 electrons. So you don't have to draw 8 dots around anything that loses all its valence electrons. So it is just taken as an assumption that if I remove all of the electrons from a valence shell and I don't draw any dots, that atom, or I'm sorry, that ion has an octet. So if you have K+, Ca2+, barium2+, sodium+, etc. If you land on 0 valence electrons, you don't got to draw any dots. It's assumed that there's an octet. Now, I'm already using the word octet here because you probably noticed that we're trying to get to 8 a lot of the time. In fact, 8 is really, really common. Now, many chemists made observations about noble gases. And that observation was they didn't really seem to do anything. They're just inert. Now, why the heck is that? Well, what do all noble gases have in common, excluding helium? Well, it was observed that, well, they're all in possession of an electron arrangement that gives them 8 valence electrons. And it turns out that when an atom has 8 valence electrons, it ends up being far more stable than it was before. So what we conclude here is that atoms are going to try to get to this stable electron configuration. Now, when I say stable, it's all relative. So something can have 8 valence electrons and be reactive, but it should be less reactive than it would be before. So what we're going to try and summarize for how atoms and ions behave is in what is known as the Octet Rule. If an atom has 8 valence electrons, it tends to be more stable. If an atom doesn't have 8 valence electrons, what it's going to do is it's going to try and get 8. So if I don't have 8, I'm going to gain or lose electrons to get to 8. Now remember that losing electrons down to 0 is the same as getting 8, because then the previous layer has an octet. like we said before. So we're going to pick the path that gets us there. Now, depending on which atom you are and where you are on the periodic table, that's going to present you with a choice. For example, and I believe that this example is going to come up later on, if I have sodium, I could either get rid of one electron, and that would give me an octet. I'd get rid of its period 3 shell. Or I could just give it 7 electrons. That would give it an octet. Which of these is easier to do? 1 thing or 7 things? And obviously the answer is we're not going to do that, because that's way too much work. Nature's going to pick the easiest choice, because nature's lazy. Just like me. So we will always have one specific outcome that happens for these, with one exception that we're going to talk about in a little bit. So let's do some examples here. Here's oxygen. Oxygen has 6 valence electrons. I've drawn their dots here. I got to either give away electrons or take electrons to get to 8. Which process will occur, and what's the result, and what's the ion that we make? So type your prediction in the chat. Disney might copyright the sound of a cat's meow. That's very possible. No, I'm more concerned that my course evaluations, which are going to go out probably next week or so, you'll get an email about course evaluations. They're going to be full of comments like, doesn't feed his cats. Or yells at cats on stream. I adore my cats. I also wish that they would be a little more quiet when I'm teaching. O2 minus is right. So here we got 6. I'm going to add 2. There they are. And what I've done is I've made the O2 minus ion. There you go. Let's do the same thing. Oh, we forgot the square brackets. There they are. Let's do the same thing with calcium. Here's calcium with 2 valence electrons. And I want to satisfy the octet rule. What should I do? Pomeranians are cats that bark. That is, well, kind of. I mean, I knew a friend who had a Pomeranian, and she loved everybody. So she'd run around and greet everybody. She was definitely a dog. So it's easier to get rid of 2 valence electrons here. So if I remove these, I get that. And there's my calcium 2 plus ion. Just like we said before, the octet is implied here, but we don't draw it for an empty former valence shell. All right. Now that you've seen it in action, here's our summary of what tends to happen. Oops, I went too far here. Elements that are on the left side of the periodic table, and I realize that group 3 doesn't really feel like it's on the left, but we do count it as on the left, tend to give away their electrons. The reason being, 3 is closer to 0 than 8, so it's going to always move in the easier direction. Elements that are in groups 5 through 7 are really close to having an octet. So what they end up doing is taking electrons to get them to 8. Noble gases are already at 8, so they're stable. And then there's this. What the heck do you do when you're at 4? And the answer is you do everything. In fact, you do so many things that we had to make 3 classes to talk about them. So, we'll talk more about carbon in Chem 261. Which, if you're not a biologist or a chemist, you don't probably have to take Chem 261. If you are just in here for engineering, you're probably good until 162 or 163. All right. So we're not going to do creating an ion for elements in group 4 because they don't really tend to form ions. And it sort of depends on which atom you have. So like carbon will tend to become negative and make C4-, but that ends up being reactive and you make other species too. On the other hand, tin, SN, will tend to become 4+, and it doesn't really follow a specific pattern for group 4, so we just don't deal with them. We're going to do the other groups instead. All right, I don't know why I had to hit a button there to make that appear, but that's okay. So, on this page, what I want you to do is I want you to tell me how many electrons get shuffled about for each of these atoms. Chlorine, barium, nitrogen, sulfur, phosphorus, and rubidium. Draw the Lewis symbol for the resulting ion, and then count how many protons and electrons each ion has after you have made it attain the octet rule. Then down at the bottom, what I want you to do is look at these ions and tell me, are these the ones you would predict to happen based on whether it has an octet rule or not as a result? Circle the ones that you expect to occur that are stable, and then draw an X through the ones that are not. Okay? I'm going to give you a few minutes to do that, and then we're going to take a break because it is currently 3 p.m. So I'll let you work on this for a bit, and then we'll break for 10 minutes after. Okay? So go ahead and get to work. Now she won't talk. She's also precariously balanced on the edge of the chair, and I'm afraid she's going to fall off. But let's go over the answers here. So, using the octet rule, for my chlorine atom, chlorine has 7 valence electrons. I would predict that I would then fill in this space right here with an additional electron to make Cl minus. And then I would have an atom that had 17 protons and 18 electrons. We do the same thing with barium. Barium starts with 2 valence electrons. If I get rid of those 2... Oh, now she's talking. We get that. And then I go to the periodic table and I see that barium has 56 protons. And now it has 54 electrons because I got rid of 2 of them. Here's my nitrogen. I'm going to fill in the octet by adding 3. So that makes it 3 minus. Nitrogen has 7 protons. And when I make it an ion, it has 10 electrons total. Now, something to note here that when I say electrons, what I actually intended was total. And not just valence. That was unclear. I'm going to quickly write down the answers to the rest of these just because we're going to run out of time if we don't, and we're due for a break in it right now anyway. I don't know how many protons it has. 37. Yeah. All right. Now, by the same logic, we could draw these ions out and see if we actually end up on this. So, for example, aluminum. Aluminum starts with 3 valence electrons. What ion would it form? Well, I would erase these 3 to get aluminum 3+. So that works. But if I go over here to cesium minus, here's cesium. If I make it minus, that's adding an electron. So this would be cesium minus. Is that what we would expect? No, because it doesn't land on the octet. So that's a no. Turns out that these ones that I'm going to cross out are no good. And this one only is bad because this path is easier. But the other ones are good. Oh, I guess it said we're supposed to circle them, so let's follow the directions because we want to get all the points. All right. Oops, that's not what I meant to do. We're going to take a break, so I need to go to the title card. We'll put the timer up on the screen. Boop. It didn't boop. There we go. Boop. Do you want to update? Nope, never. So I'll start the timer. We'll start the Mega Man music again. And we'll see you in a bit. close enough. Did Mega Man use original music? Yeah, I think all the tracks are unique. I mean, there's a lot of remixes, especially that last one that was playing. That's probably one of the most popular Mega Man themes, the Wily 1 stage in Mega Man 2. I know that's been in many games. I think that's in Smash Brothers. It's in Mega Man 2.5D. I know that for sure. All right, where are we? This slide is just talking a little bit about some elements that we're not going to draw Lewis symbols for this class. Mostly because the Lewis symbol does... Oh, excuse me. Mostly because Lewis symbols only work for elements in groups 1 through 8A. You can't really do this with transition metals, because transition metals don't follow the octet rule, so we aren't going to draw Lewis symbols for those. So the only thing that we are going to concern ourselves with for a Lewis symbol is, hey, is it in group 1 through 8A? If it is, you could draw a Lewis symbol for it. Now, in other problems, you might still need to know the charge of an ion. So, for example, if I give you the formula FeCl3, you might have to figure out what's the charge on Fe. And the way that you would do that is by figuring out the Lewis symbols for all of the other things to get their ion and what their charge is, and then calculate it backwards. And we're going to show some examples of that in the next section here, which is how ionic compounds form. I believe this is the Lonnie's lab picture or video. Let me just see here. I'll deal with it when it comes up. Okay. I'm just hoping that I have the correct link actually inserted there, so I'll have to find it. So, how do ions form in terms of like the physical process that goes on? First, let's talk about what happens after the ion forms, and then we'll talk about getting to the ion part. So if I have two ions with different charges like this, I got some cation and some anion, and I allow them to come together, they will attract and form an ionic bond. So the ionic bond is this attraction between opposite charges. Now you'll notice that my charges here... Oh, wow, that didn't show up at all. You'll notice that my charges on my ions here are not very representative of what's going on inside the ion itself. But this right here, that's red on red is not going to actually work here. This right here is the overall charge on the ion. So, for example, if I had, say, 11 protons and 10 electrons, that would equal a 1 plus charge. And so there would be slightly more positive total than negative, and that would be what this represents here. Over here, this would be an example where maybe I have 17 protons and 18 electrons for a total of a negative 1 charge. There's just slightly more negative. And the reason I picked those numbers is because I'm picking table salt. It's the most common one. So the overall charge that forms is what causes the attraction for the ionic bond. Now, if you're putting two ions together, one of them's got to be a cation, and one of them's got to be an anion. What that means is that when we make ionic compounds, I have to pair these two together, and because cations are usually metals, in fact, they're almost always metals, and anions are almost always nonmetals, ionic bonds will be between metals and nonmetals. No, it's not cation, it's cation. Unless you're from, like, Boston, then I guess you could call it Cashin or something like that. Well, if you're from New York. That was more of a British Cockney thing, I guess. I don't know. I'm not a voice actor. I do really shitty voice acting when I play Dungeons and Dragons. Only as an attempt to get better at voice acting, but that's the wrong color. All right. What does this look like in practice? So on the screen here, you can see that I'm highlighting my two ions that have been attracted to each other through the ionic bond. But in reality, a charge propagates in all directions. So if I draw coordinate axes through this, I'm going to have an attraction that goes along all of these axes in all directions. So what that means is that if this is a positive charge, it's going to attract a negative on every side of it. And each of those negatives will have a positive on every side of them too. So on average, it equals out to 1 to 1. So that's what's known as the formula unit. A formula unit is like a molecule of ionic compound. But ionic compounds don't form molecules. The ions just coalesce into a lattice that repeats forever and ever and ever. You could think of the formula unit as the simplest piece that you can copy and paste. So if I highlight one sodium ion, one chlorine ion, I could make the rest of the structure by going paste, 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 paste. You just hold down Control-V forever. Now, again, the term formula unit is used because it's not a molecule. Remember that molecules are independent entities. They float around on their own, and they don't interact with other pieces. You could have one distinct molecule. You can't really have one independent formula unit, because any other ions that are nearby would just immediately come together. And yeah, the abbreviation is FU. Isn't that great? Yeah. All right. It's not a molecule, it's FU. Now, this is the simplest formula unit for sodium chloride, and it's the only one that I really have a picture of. There's another one for zinc sulfide on the internet, but I wish they had more complicated ones. As the formulas change, the pattern also changes, and you get a different repeating array. For example, like magnesium chloride. There's twice as many chlorines as there are magnesiums, so you have twice as many green spheres as you would purple, and you get a different pattern. They wouldn't arrange like this, but they would still arrange in a repeating array. And I wish I could show you that, but I don't have a really good image of it. So you'll just have to take it with a grain of salt. Get it? It's because it's an ionic compound. Let's just keep going. So, how do these actually form? If I have these ions, they just come together and stick. But what happens if I have neutral stuff? So, like, I go to the element store and I buy neutral sodium, so sodium metal, and I buy chlorine gas, which you should not go buy chlorine gas. That's illegal and deadly, and just don't. But let's suppose that you did that already, and you decide, I'm going to put sodium and chlorine together. What will happen when I do that? Oh, I have a video for you, which means I need to... First, I gotta make sure... Oops. I gotta make sure that this is the correct video, because I used to have an old video that was, like, in 120p. And this is actually the right video. Look at that. Okay. So, window capture, that's the chat. I don't want to capture that. Lonnie's lab. There we go. So, this is Lonnie. He's kind of creepy. Which is actually the point. Lonnie works at UC Berkeley. And so this is a video of the formation of sodium chloride from its constituent elements, sodium, metal, and chlorine gas. And so this is what that looks like. So I'm not going to have the audio play here. I'm going to just talk over Lonnie, and I don't know if there are going to be captions here. There are, so let me get rid of those. Let's talk about what Lonnie's going to do here. So first he's putting chlorine gas into a container. Now, ignore the fact that he's not wearing any safety equipment, because this is what he's actually doing in the place he's doing it is actually relatively safe. Because what's going on here? At the bottom where I'm putting the cursor, this is a vent that pulls any gases above it down with very, very fast. This is basically a fume hood, but pulling gases down into the bench top. You're going to see that in a second. Any chlorine that might be slipping out of here goes straight down. This is definitely not a clean room. You can tell by the bench. It looks pretty dirty. This is probably just a classroom bench top or a laboratory bench. So this is chlorine gas, and you can tell that because it's kind of yellow. In the container over here is sodium metal. And so what the sodium metal is stored in is a sort of hexane or mineral oil solution, because sodium will react with water vapor in the air and oxidize. So we keep it in something that it won't react with. Now, Lonnie's putting it in a clean sample of mineral oil so that it gets rid of all the other mineral oil off of it, because that oil will be flammable and also inhibit the surface of the sodium. We just want the sodium in this reaction here. He's going to put the chunk of sodium into this ladle here. He's going to then heat it up, not only to evaporate out the mineral oil and burn it, which is where the initial like bright orange comes from. That's the oil that was on there. But he's going to heat it up so that it has enough energy so it becomes molten. Just a little bit molten. And you can tell when it's done because it starts to burn. And you're actually going to see this color that I've paused on the screen. This is going to be relevant for you next week because I'm actually changing the lab we're doing. Surprise. I'm going to do a more different, more interesting, and also a less work for you lab. You're going to see Samita burn things. And when you burn them, they have a characteristic color. And that characteristic color is, yeah, the flame test, exactly. You're going to see the flame test in action. For sodium, you specifically get this color. Now, this video actually has a little more orangey red than I think. Sodium is a lot more orange than that. So I think that like the color might have been adjusted just so you could see the chlorine gas a little bit better. Anyway, what we're going to do is we're going to put this hot sodium into this chlorine gas, and the reaction will immediately start. The heat is not only to make it molten, but also to sustain the initial part of the reaction. And there it goes. Now you can see the gas coming out, and it just gets sucked straight down the vent. So Lonnie's in no trouble here of breathing in any gas that escapes. What he's making is gaseous sodium chloride. So this is table salt in the gas phase, which you might think of as like, what the hell? Table salt is a solid. Why would you make it a gas? Well, it's got to become a gas to start. Eventually, what will happen when the reaction is done, there's so much energy in the reaction that, and you can see how much energy was in there. It made the ladle that hot. It's red hot. There's so much energy in there released from the formation of these ions that it vaporized everything. And eventually it will cool down and settle into a white powder. And you can kind of see that at the bottom here, I think. Now, he doesn't let that go for long enough, unfortunately. Instead, what he does is he just pulls out a sample that he made earlier from underneath the benchtop and then eats it. So here's his sodium chloride that he produced earlier. This right here, this white salt, is actually from here. Once this distills all the way down. And no, Lonnie, don't eat it. Don't eat in the lab. This is a safety violation. We're going to have to report you. Don't eat your chemical reactions. Like, don't do this. Don't do it. No, Lonnie, don't. Oh. We're so disappointed. All right, so that's what it looks like when an ionic compound undergoes a reaction to form a lattice. Now, why doesn't this happen outside, like, say, in the ocean or in the earth or whatever? And the answer to that is it did already happen. It happened millions and, well, billions upon billions of years ago when these elements were first formed in the cores of stars. That was salt on a hard-boiled egg. Or, I mean, I don't know, Lonnie. Maybe he would put salt on a marshmallow. So, I don't judge. Actually, I will judge. In fact, I was just judging. All right. So, what happened here? This is what's known as an electron transfer. When you have neutral sodium and neutral chlorine, electrons get moved around. Now, how do the electrons get moved around? Well, let's draw their Lewis structures and see if we can figure that out. I have sodium here with 1 valence electron, and chlorine, I didn't mean to actually click that, with 7 valence electrons. Now, is there a way I could move my electrons around so that I have the octet on everybody? Well, if I take this guy and I put it over here, then sodium would have an octet because it would have 0, which counts as an octet. Chlorine would have 8 valence electrons, which would count as an octet. They would both have an octet, so they'd both be more stable than they were before. And then the resulting 2 ions, because they have charges now overall, would then attract together to form an ionic bond. I grabbed the felt tip pen there instead of the pen. So for all reactions between metals and nonmetals that can form ionic compounds, we just move their electrons around until everybody has an octet. So that's our goal. Can you shuffle electrons around such that everything has an octet? And if you can, what you have is the ionic compound that forms in terms of its formula unit. So, first, shuffle electrons around, and then allow electrostatic forces to create the ionic bonds. Easy enough. Now again, we always have to have a metal, and we always have to have a non-metal here. This is going to become really relevant when we are doing naming in Unit 11. Remembering that ionic bonds are always metals and nonmetals. So let's make some ionic bonds and try and figure out some formulas here. The only thing that I really care about, I guess there's 2 things, which are the ones in color. So whenever you write the formula of an ionic compound, you always put the metal first. We put the positively charged thing first. That's convention. And if you have done your electron shuffling correctly, when you count out the charge of all your ions, the total charge will always be 0. So if I make a formula out of these ions, the total charge has to be 0. So in order to have 0, I would have to have 1 of each. If I had 2 of each over here, for example, this is the formula that I would get, and that's not neutral. So this is not the formula unit that occurs. Formula units must be neutral. If they weren't neutral, they would attract other ions, and then the formula unit would change. So what would the formula unit be for these 2 right here? Potassium and sulfide. Well, let's write them out. If I combine them, I get Ks. -2 and +1 will sum together to be -1, and that would be my unit. Well, that's not a valid formula unit because I have an overall charge. So it's going to attract other things to change that formula unit and also change its charge. So what would it change to? Well, I need another positive, so we'll do this. That changes my formula unit to K2S. That's the wrong pen. There you go. And that's the formula unit. That was a terrible circle. Good job, me. Ah! Everything is falling apart here. There you go. So that's how we construct formula units. Put your ions together, see which piece you need more of, and keep combining the pieces until the entire thing is neutral. You can't read what's on the screen there, so I'm going to erase all the ink. There you go. Okay, now that you have the gist of it, let's do this for transition metals where we don't actually know the charge on the metal. We're going to use this strategy to solve for transition metals. Now, you can't draw a Lewis symbol for them, but the Lewis symbol is just to get us to figure out what the charges are for some ions. For example, if I said, I'm going to combine this and this together, and I asked you to figure out the charges, well, you could say, okay, chlorine has 7 valence electrons. I need to put in one more to get it to here. And that's how you get the charge. You do the same thing for barium. I need to get rid of these guys to get it to here. And now I can make a formula out of it, because I'll need a second one of these to become neutral. So that's the process for two elements that have that are in groups 1 through 8A that we know. But what would happen if I did something like this instead? So let's get rid of this to make some space here. What if instead of barium and chloride, I picked, I don't know, let's say iron and chloride? What would they combine to make? Well, let's see here. We know that this would do the exact same thing, right? But what does this do? And the answer is we don't draw a Lewis structure for it, so we need more information. So let's suppose that instead of having an unknown product, we had this is our formula. What that means is that when I get down to this part down here, I have Cl minus and I have Fe with an unknown charge. Now if I got 3 of these, the whole thing has to have a charge of 0, right? So this has to be neutral. This whole thing. So what goes in the question mark? If I've got -3 charge, how much positive do I need to balance it out? It's got to be 3. So on the left here, we took elements and turned them into a formula. On the right here, we take the formula and then can turn it back into elements, or ions, I should say. So for transition metals, you have to follow this sort of approach. You're not going to have this information to work with, so you have to use the formula in order to figure it out. So let's do another example with iron and oxygen here. Here I tell you what the ions are, so let's make the formula out of them. Here's my charges. Is it neutral? It's not. So that's not going to be the formula unit. I need more negative, so let's do this. So that's going to give me an overall minus. That doesn't work either. So now I need more positive. That's also not going to work if I do that. So I need another negative. And it turns out that that does work. So if I turn my formula into this, Fe2O3, I get a neutral ionic compound. And also a whiny cat. Hi. Yeah, I love you. So that's the process for taking these ions and turning them into a formula. Put them together, see what you need more of, and just keep doing that until you figure out the formula unit. Now, let's suppose that you wanted to go backwards instead. Maybe I showed you the formula. I gave you this instead. And I said, what ions are used to make this? Maybe this text isn't there. Well, you always know what ion oxygen will form because it is in group 1 through 8A. We know what ions those form, and we can use the octet rule to figure that out. Remember that oxygen would have 6 valence electrons. I would add 2 more to get my ion that forms an octet. Iron is not a group 1,8 element, so we cannot do that strategy with it. But we have enough information to solve for it. So I have 2 irons here. And I don't know what goes in the blank here. And I have 3 oxides. O2 minus, O2 minus, O2 minus. The whole thing's got to be neutral. I've got a charge of 6 minus here, and I've got 2 of something. What must that something be? Well, when you do all of the math, it's got to be positive 3. So that's how we go in the other direction. You're always going to be tasked with either taking the ions and making the formula, or taking the formula and then making the ions out of it. So you need to go in both directions to figure out the formula of the ionic compound that forms. So let's clear that and put all the text on the screen here. There you go. All right, now that you've seen it in action, what I want you to do is construct these formulas for these different elements. First, turn them into ions, then make the formula unit. You'll notice that none of these are transition metals. Those are on the next screen here. And then we're going to reconstruct all these ionic compounds, or deconstruct them back into ions, in a slide later on. So let's start here. I'll have you write the formula, predict the formula. Type your formula in the chat. I realize you can't do subscripts. That's okay. Do it the best you can. I'll see you in a bit. All right, let's go over the answers here. So if I were to write the formula units of these by first writing the ions, here are the ions that form for potassium and bromide. And if you want to see how these ions form, you can go back to the earlier in today's lecture. Since I have one of each charge, I should get KBr. For calcium and oxygen, forgot my 2 there. Calcium is 2+, oxide is 2-. I need 1 of each to get that. Magnesium, I can make it 2+. I accidentally wrote mark there. Chlorine is a -. +2 and -1 do not make 0, so I'm going to need extra negative charge. And then there's my formula, MgCl2. For sodium and nitride, I need to put a bunch of positives here. Sorry. Every time I see that, I break into the Batman song. There you go. And then this one down here, there's only one combination that works, and that's to do this, to get 6 of each charge. There you go. All right, so on the next slide here are some more exercises of putting these transition metals together, or these other metals that are available. There's only 2 transition metals to make a formula. I'm going to have you do those on your own. And also these next few slides up here, because these are just doing the reverse of what we did. So for anybody who's watching in the future, you can go ahead and pause the video. I'm going to go back to that previous slide. So I'm going to just put the answers here really quickly so that you can do these problems on your own, because we're out of time for today. So let me just have the formulas on the screen here. So these are each for these. And again, you can hit pause to copy these down if you'd like, but then I'm going to go to the next slide here and give you the ions here for your answers. Now my cat is not actually meowing. I just am imagining her meowing because she's been meowing all day today. That's not gold, that's aluminum. Hey guys, I turned gold into aluminum. I put bromine. Okay, chlorine into bromine is a little less egregious, but gold into aluminum is not quite good. Thank you. And this is scandium, and that's not even the right charge. There we go. There you go. There's the answers to those. So ideally, you will have paused the video and done these problems if you're watching this later on in the future. If you're watching this right now, you can always just stop me from talking by hitting the spacebar and pause the video and do these problems then, or rewind a little bit after the lecture is over. But I believe that is it for monatomic ions. We're going to come back and talk a little bit about polyatomic ions. Yeah, remember those polyatomic ions that I said, hey, you're going to have to memorize these. I'm I mean, technically not for online, but you're going to want to have those handy because we're going to work with those next time. All right, I'm going to put the title card up, and then I'm going to do this, which is going to look kind of strange. We're going to add something on top of the title card here. What? I want a window capture. We'll just window capture 4. That's fine. We're going to put this on the screen here. This is the current schedule for the quarter, and you'll notice that we are right here in week 6. This was today. Tomorrow, it says extra lecture if needed. Hey, guess what? We don't need it. There's no lecture tomorrow. There's also no lab lecture tomorrow, so there will just be nothing. You get a day off, but I will be available for you to send me emails for questions as if it was a QA. I'm just not going to have a stream. I'm going to let you guys have a day off because you did just take an exam. And I'm also going to try and grade your labs so that I can get them done. And I'm also going to try and get that lab right up for lab number 3. So I will be working, but we're not going to actually meet. So enjoy your day off. And we will reconvene on Thursday where we will finish Unit 9. We'll probably start Unit 10, which means we're going to be ahead of the schedule anyway. Unit 10 is not very long. And then once Units 9 and 10 are done, I will then post the quiz for those 2 units together. So in the meantime, please enjoy the rest of your evening. I will see you for class again on Thursday. And I hope that you have a good day today and tomorrow until then. Cheers. I was trying to like drag all that out so that I could get the little outro set up, but I'm just bad. There you go. See you later.